Hello community, so great that you are back. Today we have a new RAG 3.0, LeanRAG. You know, normally we have documents, great, then we build a knowledge graph, and then we have some RAG and LLM and agentic RAG and whatever, and it just works, but there is an inherent problem to this architecture. We do have semantic islands and we have other kind of problems I'm going to explain in a minute. So the idea now is to have a new architecture, what they call a LeanRAG system. This is a new retrieval augmented generation RAG framework that builds now new knowledge graphs. It sounds crazy, no? We have our documents and now we co-design a new knowledge aggregation, a hierarchical knowledge aggregation of multiple knowledge graph, and we define a new retrieval strategy for an advanced RAG system, RAG 3.0. So, you mean this sounds like a lot of fun? Absolutely, I can tell you. The AI tells now, hey, you know what? I will redesign my data structure of my external data that are here configured in a normal flat knowledge graph before I will retrieve them with a new RAG 0 optimization that will simply amaze you. We will solve two problems. We will solve the problem of a semantic island that we have in flat knowledge graph, and we will solve the problem of structure unaware retrieval methodologies in the classical graph RAG system. You could say now that we generate explicit intercluster relations, and we will introduce a common or a lowest common ancestor, an LCA-based retrieval strategy to build more precise, more compact, and more contextually comprehensive sets of data. Or if you want to have it a little bit more scientific, we will have here or infer explicit intercluster summary relation, leveraging here the underlying knowledge, a contextual and the relational semantics to establish here higher order abstraction. You know, I'm talking here always about complexity levels. So you might say, hey, wait a minute, there's something. So you mean higher order abstraction? Is this what you were talking here in this last video about a hypergraph RAG system, where we also focused on not just building smarter agent itself, but we had a symbiotic system where we had to care about the agent and we had a co-evolvement here of the agent and the knowledge environment itself? Absolutely. This is exactly now. We continue here, if you want, this agentic hyper graph RAG with reinforcement learning graph R1, and this is now the next RAG system that even pushes it further. Now, a lot of you told me, hey, Notebook LM, have a look at this, beautiful. So here we have it, and why I cannot use Notebook LM. Look, I have here my two sources here, the LeanRAG and the UR2 PDF, both videos here. And then I ask, hey, build a mind map, and you see what happens? I just get here new trees. I have never a cross-link between the tree or a tree branch. And therefore, I mean, it's crazy, no? It's LeanRAG. It is about interconnected clustering, and the output itself, the instrument currently for Notebook LM, is not able to show me here cross-links that I have cross-references. And I tried here this system, is it able to detect that this is more or less on its base a hypergraph structure? And unfortunately, it failed. You have to look here at the text. And you see here, if you then go here to Notebook LM, it simply failed to understand that there's on a deeper level a thematic connectivity between those two papers. But hey, luckily, we human, we immediately saw this, no? So therefore, our agentic hypergraph RAG, this is here where we continue now. Now, let me start with some advanced stuff, going here to a mathematical hypergraph. If you don't feel comfortable, if you say, hey, I'm just beginning with AI, just skip the next 2-3 minutes. I tell you exactly when the advanced stuff ends, and we go back here to the normal, simple explanation of AI. Definition of a hypergraph is clear, and then where does the LeanRAG methodology really resembles a hypergraph? So therefore, you immediately can say, hey, I understand it here. Great. So it resembles a hypergraph that clusters are hyperedges in a hypergraph. And the intercluster relations are hyperedge intersections. And we do have a hierarchical lifting. If you are not really familiar, this is the explanation, what I mean with this. But also careful, there is now where the term LeanRAG diverges a little bit from the pure definition of a mathematical hypergraph. This is about the LLM synthesis, I explained this in a second, the retrieval procedure, and a very specific token minimization objective that is not normally part of a hypergraph. LLM synthesis clear, no? The LeanRAG introduces now semantic abstraction. No? So we have a semantic compression, which is not a typical hypergraph here in mathematics, and retrieval procedure, of course. Plus here the token minimization, as I told you, a pure hypergraph model don't encode this retrieval budget minimization. But I think if you understand it, this is so easy because you immediately see, oh, this is a hypergraph algorithm, and this analogy is really useful. Hypergraph terms making here the LeanRAG less ad hoc. So what it means, the clusters that we have now in LeanRAG are hyperedges, the intercluster relations are the hyperedge overlaps, and the, if you want, lean graph retrieval procedures or approximate Steiner subgraphs in hypergraph incident structure. We have them from the algorithms. You could use alternatively the hypergraph partitioning. Instead, we will use here GMM for the aggregation, minimal hitting sag, and then, of course, spectral hypergraph embedding to replace the flat dense retrieval embeddings. And if you say, hey, has this anything to do with the video where I explained the wavelet operator theory, where we could go very easily beyond GPT-5? Yes, exactly. This is all interconnected. So therefore, if you want summary, LeanRAG can be, if you are familiar with this, understood as an applied semantic hypergraph compression and retrieval system. The novelty is not in the mathematics of the hypergraph themselves, because this is known, but in the co-design. Again, we have the co-design of a semantic aggregation function. I will explain those two functions in 2 to 3 minutes in detail. I will give you the exact prompt, and the co-design of a retrieval sequence optimization via an LCA traversal. So we have now minimal subgraph problems under a constraint like a token budget constraint. This is it. End of advanced. Never mind. Welcome back. So this is now the new publication, August 14, 2025. LeanRAG, knowledge graph-based generation with semantic aggregation and hierarchical retrieval. So you see from our classical RAG, there's nothing left. We are in the third generation of RAG, and RAG is here multi-agent, hyper-intelligent, and what else? But now LeanRAG says, hey, listen, the data that you give me in my input, I can't use the data. I have to modify the data. I have to modify my interpretation of the environment that I, as an AI system, interact with the environment as an agent. So therefore, a novel retrieval augmented generation framework that synergistically integrates deeply collaborative knowledge structuring, a redesign of the knowledge of the environment with a lean, therefore a LeanRAG, structure-guided retrieval strategy. We have, again, a co-evolvement of the data structure and the retrieval strategy on this knowledge graph. Beautiful. From the authors here, you have RAG with graph, then you have here LeanRAG, and you see immediately what is the difference. We will have a look at this in detail now. What I just want to show you here, the knowledge graph aggregation of LeanRAG. This is so nice. So we will start here, if you want, if we build here this LeanRAG architecture, we will start with clusters, and then we see if we find here some superstructures on these clusters so we can condense these clusters in a very intelligent way. We have clusters of clusters and superclusters and so on, and therefore we become here, if you want, semantically integrating higher levels of complexity so you can search a graph in multiple dimensions. You do not just have here the width of a graph here on a flat hyperplane, but you also have a hierarchical structure. So this means we will have multiple layers here of a knowledge graph itself. And it sounds easy, but unfortunately it's quite complicated, especially if you have a deep dive into the mathematics. But we will make it super easy. So what is it? A novel semantic aggregation algorithm designed for superior knowledge condensation. So we rearrange here the data that we retrieve here from a database, from the external whatever. We have to rebuild the data representation. So this method constructs a multi-resolution knowledge map by modeling and building new relational edges, remember, hyperedges, between summary level conceptual nodes, effectively preserving here both the fine-grained facts and the high-level thematic connections within a single coherent graph structure. Sounds easy? Well, let's have a look. There are two main steps. This is step number 1, the hierarchical knowledge graph aggregation. Foundation of LeanRAG is here, and this is a screenshot because it's absolutely clear. This is I cannot do this any better. This is absolutely, I say, yeah, this is the wording, you have to learn it. The foundation of LeanRAG is the transformation of a flat knowledge graph, G0, into a multi-level semantically rich hierarchy. This hierarchy allows for the retrieval at varying levels of abstractions. I talk about complexity levels. We construct this hierarchy, the authors tell us, denoted here as H for hierarchy, from a G0 to a GK, in a bottom-up, layer-by-layer fashion. So each layer, GI, represents here a more abstract view of the layer below it, GI-1. The core of this construction lies in a recursive aggregation process that clusters now the nodes based on the semantic similarity and then, quotation mark, intelligently generates new, more abstract entities, hypernodes, and relations from the next layer. So again, you see semantic similarity and say, oh no, oh yeah, but never mind. Interestingly for you to immediately understand from a knowledge graph here, now we have a multi-layer knowledge graph, which is something beautiful, but at first we have to build it. So how do we do this? Give me a knowledge graph layer, GI-1. The first step is to identify a group of semantically related entities that can be abstracted into a single higher level concepts. We leverage here the rich descriptive text, D for the description here, associated with each entity, V for vertex, for this purpose. And how we do here the clustering of text? Yes, you know it, we have a Gaussian mixture model. Now, if you are not familiar with this, I would recommend you this particular paper. This is from Tokyo Institute of Technology in Japan. Gaussian mixture model. This is now applied to the Q functions for the reinforcement learning by a Riemannian optimization on a Riemann hyperplane. Real nice. This is one of the most interesting paper I found on this. So if you want to know here the novel role for the Gaussian mixture models here as functional approximators of the Q function losses in reinforcement learning, I would say have a look at this. And you know what is also the beauty? Deep Q networks, everything you know about here, reinforcement learning. This is more or less just 2 pages. Those are the 2 pages that you have to understand. Now, honestly, it took me several days to understand this because I have to tell you, I hope you're more intelligent than I am, but it was not that easy. This was quite a condensed representation of mathematics, but it explains so many things. So if you have 4 or 5 hours, or maybe you need just 20 minutes, have a look at these 2 pages, you will understand everything immediately. If you say, hey, I'm a beginner AI, never mind. You know K-means as a methodology, no? When you assume in your clustering algorithm that you have spherical clusters. The form of the cluster is a spherical shape. Great. You know, and now GMMs are nothing else like K-means. Just with GMMs here, because you have a covariant component now, we can adapt now to ellipsoid shapes here of the clusters. That's it. That's all there is. You see, it can be simple. Now, careful, GMMs assume that you have at first enough data in each cluster. Be sure about this. Plus, second constraint is those data here and those data points follow here a Gaussian distribution. Please, especially in the real world data, this is not always the case. You have to be extremely careful. I tried this out several times. I completely failed, and then I looked at my data distribution. I said, okay, not at all Gaussian. No? Real world data can be unpredictable. So careful, if you use this methodology, you have to have Gaussian, well, a Gaussian distribution. And if you absolutely say, I don't know what to use, I then in this case use dbScan. Maybe not as advanced, but you know, this is something that works almost the time. Everything is already coded for you. You don't have to code anything at all. Here, scikit-learn, Gaussian mixture. Here you have it as a particular class. Everything is defined with all the parameters you can ever dream of. Everything is already ready for you. You just have to understand what's happening here. Okay, so we have two parts. I told you now that we have a little bit more of a technical understanding. Let's have a look at the first part and then at the second part in a little bit more detailed level. So first part, hierarchical knowledge graph aggregation. We build our dream graph. I had a discussion with my GPT-5 system. I had other papers, then I cross-read this, and then I found here that GPT-5 did a beautiful work here summarizing the discussion. So I just take a screenshot of my GPT-5 here because this is what I achieved with my companion GPT-5 after some hours of discussing this paper, singular. So what is the flow of this? You start with a base knowledge graph, no? A flat knowledge graph that you're familiar with. Nodes and edges, the entities and the relation each carry short textual description. Now the goal that we want is to transform this G0 into a multi-level hierarchy, where the higher layers compress and organize here the lower level semantics. So to encode now these entities for semantic grouping, for the current layer Gi-1, encode every entity's description D into a dense vector. We have an embedding, we have a vector field. This produces now an embedding set that will drive here the clustering. Now we have to cluster semantically similar entities. As I told you, we use here the Gaussian mixture model. Beautiful. And then synthesize the aggregated parent entities per cluster. So for each cluster Cj, form one higher level aggregate entity alpha j with a concise name and a description D alpha j that summarizes its member nodes and its intra-cluster relations R Cj. Link every original entity from our vertices to its new parent alpha j to establish a hierarchy vertical parent-child edge structure. And this step uses an LLM-guided generation function fEntity. I will explain this in a moment. Under a constrained prompt, I will show you this prompt in a moment. So the aggregator reflects only evidence presented in the cluster. No hallucination. This is a real hard constraint here. You only work with the presented data. You can have, of course, hallucination if the LLM just goes yippee crazy, no? But you should reduce here the hallucination because you don't rely here on parametric knowledge. You provide the information, the knowledge to the LLM. First part. Second part, we go on, point 5. Then we create explicit relation between the aggregates to avoid here, we want to have no semantic islands. No? So for any pair of clusters, Cj and Ck, collect now the original intercluster relations, and you say, my goodness, what is this? Edges whose endpoint lie across the two clusters, and we will define a connectivity strength lambda jk, and if lambda jk is greater than tau as a specific threshold that we can define, summarize these crosslinks into a single higher level relation, using here another LLM function. I will show you this function. I will show you the prompt for this function. Never mind. And if this is not larger than, otherwise keep a lightweight concatenation summary of R. So this yields the horizontal edges among the aggregates in Gi, preserving here the reversibility and the cross-community semantics at the higher layers. And then materialize the next layer and repeat. So we assemble now Gi with all the vertices, the newly formed aggregate relations, and their description. Then we iterate here the steps 2 to 5 again, bottom up, until reaching here the desired coarseness or a single root-like layer. What we end up with is a result is a navigatable multi-resolution knowledge graph in which both vertical, so that means the abstraction, and the horizontal, so the cross-aggregate structure, are explicit and we can work with them. Yeah, you have control and hyperparameters and the cluster size. You can manually override the cluster size here, or tau here in a particular threshold. You can play around with this, so you can adjust those hyperparameters to shape here the abstraction strength and the density of the high-level connectivity. This function f that I just told you here in this complete flow, let's talk about now a detail. So the generation function fEntity is implemented here And you're not going to believe it, not with a mathematical formula. I mean, yeah, of course you can write it, but by an LLM. And this LLM, but you need a very specifically designed prompt for this, that you get here a function entity. Yeah, here's the explanation. Great. What I want to show you is the prompt that the authors use, because this is interesting. Yeah? So this is the entity aggregation analyst, the role, and you have the entity aggregation prompt. This is the prompt. You find this in the annex of the original paper. Have a look at this. It's absolutely fascinating. Just give you here some short insight. The goal, invent a meaningful aggregate entity that represents here the set. Name, no duplicate. Great. The grounding rule, everything must be based only on the provided entities on the relations. Reduce the hallucination to the max. Naming rule, you have to be careful. You have a clear JSON discipline for a programmatic extraction here of alpha j and the description of alpha j, and output pure JSON with the field. The entity name becomes your alpha j, the entity description becomes your d alpha j, and the finding is here an array of summary and explanation items that capture the ground property of the clusters. So an LLM does this for us. What a surprise, no? And then, if we have all of this, what we do? This post-processing here of step 1 and the graph updates. I told you, the system will now reconfigure the data it found on a knowledge graph, on a graph network structure, or even coming in from data streams from environment, and it will find a new optimal representation of this external data. Because it will co-develop here a new methodology, LeanRAG, that it can then extract in a perfect RAG3 system for specific tasks, specific answers from those texts. So post-processing, we validate the JSON, we create a node alpha j with the description, d alpha j, we wire here the parent-child edges here for all our vertices, establishing a layer-to-layer mapping. So we go from the layer gi minus 1, we have a connection now to gi level. Then we have, optional store findings as node attributes to support later relation synthesis and auditing. And this completes here the entity side of the hierarchical aggregation, part 1. Now the intercluster relation, the aggregation here is generated separately. And we will use here another function f relation, using also a dedicated prompt. So let's jump over to part 2. Yeah, in practice, general function f-related is implemented by LLMs guided here by a specific prompt. Here you have what I would explain to you in a beautiful screenshot from the original paper to prevent the formation of semantic islands. At the higher layers, we explicitly create a new relation between the aggregated entities in VI. This ensures that the graph remains connected and navigatable at all levels of the abstractions. This here is not a relation aggregation prompt for your super LLM that they used here. Beautiful. So yeah, you have here the profile, the skill, the goal, the input name, the output format defined, plus a lot of rules, and give an example for your particular domain knowledge and for your particular complexity of your human task. By recursively applying this process of clustering and generation, LeanRAG constructs now a rich multi-layered knowledge graph. Multi-layered knowledge graph, where each layer of the knowledge graph now provides a progressively more abstract, yet semantically coherent view of the original data, of the original information, of the original knowledge. Part 2. Now comes the retrieval in the RAG. Given our user query, the first step is now to ground, because up until now we just redesigned here the data structure, the data representation for this new LeanRAG. Now we have a user query, now we have to operate on this new data representation. First step is to ground the query in the most specific fine-grained facts available. So we have a dense retrieval search exclusively over the entities of the original graph, including the initial entities, that is the base layer graph G0 or GO. We identified the top n entities whose textual description are mostly semantically similar, cosine similarity, to the query complexity. And we call this the seed entities. Sounds familiar? Yes, of course. And then, in the contextualization via an LCA path traversal, we have now that LeanRAG utilizes now the entire hierarchy H to define a much more focused and meaningful context. So the core idea is now to construct a minimal subgraph in this hierarchy, not on a single flat knowledge graph, but in the complete hierarchy that connects here the seed entities from G0 through their most immediate shared concepts in the hierarchy. So we climb up and down the hierarchy. So this means for two seed entities in VSeed, their lowest common ancestor, vertex LCA, is defined as the common ancestor with the minimum depth in the hierarchy that we defined among all the ancestors. So this ensures that the combined path length from the two seed entities to VLCA is minimized to avoid information redundancy. We have the best form, the best shape, the best representation of the data. It is not that trivial, but let's have a look at this. So this retrieval path that we find is then defined as the union of all the shortest path in the hierarchy from each seed entity V to the common ancestor. Great. Where, the shortest path, guess what, is the shortest path between the two nodes within the hierarchical graph H. And since our hierarchy is tree-like, this path consists of the direct chain from child node to parent node. Finally, the retrieved subgraph for RAG context, G retrieved, is composed now of all the entities and all the relations that lie in those LCA paths. And therefore, we achieved our goal. Wow, you see we have here LCA and we have the intercluster relations. So this is what we are looking now forward if we have higher complexity levels. Now we can handle them in a hierarchical knowledge graph. Don't ask me how I imagined this mathematical object, how it could look like. I thought about doing some graphical visualization, but it all failed, so maybe in one of my next videos. This is what GPT-5 in my discussion with GPT-5 came up as a pseudocode. I don't know if it really helps you after this verbal instruction, but maybe you are absolutely perfect if you see a pseudocode and you immediately understand it much better than in any other way. So this is the pseudocode for you. I also ask you GPT-5 to generate here a minimal but real concrete example. So this is it. Suppose CJ contains here the entities and their edges extracted here from some documentation about Spark. So the entities we have Spark Core, Spark SQL, mlib, structured streaming, Spark on Kubernetes, and the description intra-cluster relation include is component of, extends and provides an API for. Prompting here returns the entity name, the entity description, and the findings. So this means at the end, programmatically, you can set alpha j equal Apache Spark, compute an analytics stack, attach here the alpha j as its descriptor, of course, and link all 5 sub-entities to alpha j. So this forms one supernode, a GI, that Retrieval can hit as a shared anchor still for diverse Spark-related seeds. Maybe it helps you. You have the complete code, the complete GitHub of LeanRAG available for you. Here you have it. This here is your GitHub repo. You have here step by step from document chunking, extracting triple entity description here, then graph rag, and then you have built the graph here and the retrieval process. Everything is already ready for you, coded for you. I will have a look at this myself in the afternoon, but I just wanted to show you this is here, the repo for you. Performance. Let's talk about the performance. After all this explanation, you might say, hey, wait a minute. Is this new methodology worth it? What are the results? What are the benchmarks? Here. For different data set, 1, 2, 3, 4, from agriculture to legal to computer science to a mixture of everything, 4 different metrics. And here you have now the new LeanRAG, and this is compared to other RAG system like HiRAG or GraphRAG or LightRAG or FastGraphRAG or Naive. And here you see now the performance, the benchmarks. For agriculture, 3 out of 4. Hierarchical seems to be here also very good. Legal, 3 out of 4. GraphRag is here also sometimes leading. Computer science, well, 2 out of 4. Naive is even better, unbelievable. And for a pure mixture here, LeanRAG, 4 out of 4. But just have a look at the numbers. No? They are real close. So I don't know, you have really, for your particular domain, for your particular job, you have to test this out. Go with a simple GraphRag implementation, go with a hierarchical implementation, then try here the code of LeanRAG and see in your use case, is it really worth here this additional layer of complexity and this building up of multiple layers of a knowledge graph? Does it really pay off if you look here at the benchmark data? Summary. Again, looking back, what we have here achieved. I told you we have 2 main blocks. The first block was the hierarchical knowledge graph aggregation. Before we do anything, we just build here a new graph. We have 3 steps: the clustering itself, the aggregated entities, and the aggregated relations. Clustering, clear, entities are embedded into vectors, high-dimensional vector representation via any encoder you can find. Sentence, birds, great. Embeddings are grouped using here a Gaussian mixture model, GMN, into semantically coherent clusters, or go with dbScan or anything else. Each cluster is abstracted into a new aggregated entity on a higher level with a synthesized description, as I showed you, generated by another LLM. And then we have aggregated relations. And yes, of course, you feel that it is similar to a hypergraph. To avoid here the semantic islands, the lean graph infers the explicit intercluster relation. I think this is one of the powers that we see here with LeanRAG, this intercluster relations. If 2 clusters have a strong enough cross-link, and I showed you here the threshold parameters, an LLM generates here a higher level relation that will now serve here as a basis for the RAG extension. So this recursive process here, the first step, yields here a beautiful multi-resolution semantic network of multiple layers of complexities. The second main part is now the structured retrieval, the RAG part if you want, the R part, via here LCA traversal. So retrieval processes button up for a specific human query queue, find the top n seed entities in the base graph G0. Instead of retrieving now all the path between the seed nodes, LeanRAG climbs here the hierarchy and connects them via the lowest common ancestor, and this ensures the retrieval is minimal, contextually coherent. And the final subgraph we end up with is the retrieved subgraph G retrieved contains now the node and the relations among all those minimal LCE paths, and don't forget the relevant intercluster relations. So quite a complex adventure, but what we gain is it creates here a narrative retrieval context, a fine-grained facts, plus there are broader conceptual ties, but with redundant noise simply stripped away. So this is where you can reduce up to 50% of the redundancies, and you have less hallucinations, and maybe, and this is I have to test out, you can maybe increase here to higher complexity in an easier way because you do have a co-evolvement of the retrieval strategy. This is coupled or co-evolved here with the new representation of your input data. Any final thoughts from your side? If not, I do have one. I think this is really important. I mean, at first I thought another RAG system, come on, this is not important, no? But I think this is significant because it shows how the graph structure and the retrieval functions should be co-designed and not decoupled from each other. It provides a little bit complicated and mathematical sound framework, if you really have a deep dive, that can scale to long domain-specific documents. If you have legal corpora or a technical manuscript here, thousands and thousands of pages here with a better accuracy and a better efficiency. And I think it really opens here new pathways for future adaptive retrieval systems. So where the knowledge graph continuously evolve with an LLM feedback here. So RAG and agentic system, it will more or less all become one huge AI complexity in itself. I don't know if we have then a fixed border between an LLM and an agentic task here, a knowledge graph on multiple layer that is in a fluid flow of knowledge transformation. My goodness. I hope you enjoyed it. If you like this kind of videos, hey, why not subscribe, and I see you in my next video.